Assalamu alaikum wa rahmatullahi wa barakatuh. Today we'll do Theorem 10.1 of the circles, which says equal chords of a circle subtend equal angles at the center. Equal chords of a circle subtend equal angles at the center. See, that means if I have a circle and if I will make a chord like this, let us say this is one chord, and if I'll draw one more chord which is equal to this chord anywhere, for example, I'll do like this. This chord is equal to this chord. Let me name them. For example, this chord is AB and this chord is PQ. These are two chords which are equal in length. AB is equal to PQ. This is the center of a circle, let us say O. Now what I have to prove, we are going to prove that these equal chords subtend equal angles at the center. Angle subtended by the chord means, if I join this is the OA radius. If I'll join this, if I join this and this. Now, angle subtended by AB at the center is this angle. Angle subtended means angle बनाना center पे AB से. AB कौन सा angle center पे बनाएगा उसको कहते हैं angle subtended by AB at the center. Similarly, chord PQ will subtend this angle at the center. And I have to prove that these angles are equal. That means equal chords subtend equal angles at the center. Given. What is given? A circle with center O. A circle with center O with AB and PQ its chords. With AB and PQ its chords such that AB is equal to PQ because chords are of equal length. To prove, what we are going to prove? We are going to prove this angle is equal to this angle. Angle AOB is equal to angle POQ. Angle AOB is equal to angle POQ. Now let us prove this. Very easy proof. Let us consider this triangle and this triangle. Consider triangle AOB and triangle POQ. Triangle AOB and triangle POQ. Since if you see these two triangles, OA OA, I can say OA is equal to OQ. OA is equal to OQ. OA is equal to OQ. Why? Because radii of the same circle. OA is radius, OQ is radius as well. So OA is equal to OQ. The reason is radii of the same circle. Similarly, we can say OB is equal to OP. OB is equal to OP. Radii of the same circle. Radii of the same circle. Then I can say AB is equal to PQ. AB is equal to PQ. Reason, it's given. Therefore, triangle AOB is congruent to triangle POQ by side, side, side. Side, side, side congruency axiom. By side, side, side congruency axiom, we proved that triangle AOB is congruent to triangle POQ. If that is the case, then I can say angle AOB is equal to angle POQ. Angle AOB is equal to angle POQ by CPCTC. Because these are corresponding parts of congruent triangle, and we know that corresponding parts of congruent triangle are congruent. And that's it. We had to prove angle AOB is equal to angle POQ. So we are done. Hence, proved. Okay, make a note. Let us have one more theorem. Theorem 10.2 says if the angles subtended by the chord of the circle at the center are equal, then the chords are equal. Now it's the converse of 10.2. You can do it easily by the same logic, by the same procedure. Make two triangles, then prove them they are congruent. Then by CPCTC you will get the result. And I'll show you 10.3 theorem, because 10.2 is easy, you can do it similar as you did the 10.1. Now 10.3, the perpendicular from the chord of a circle to a chord bisects the chord. The perpendicular from the center of a circle, from the center of a circle, the perpendicular from the center of a circle to a chord bisects the chord. To a chord bisects the chord. This is our next theorem, which says if you draw a perpendicular from the center of a circle to the chord, it will bisect the chord. What does that mean? For example, if I have a circle like this with center O, and I have a chord like this, let's say AB, and if I draw a perpendicular from the center to this chord, just like this is a perpendicular. Now what this perpendicular will do, it will bisect the chord. That means if this point is P, so AB is equal to PB. This is what we need to prove. What is given? A circle with center O. A circle with center O with AB its chord, and OP is perpendicular to AB. To prove what we are going to prove, that perpendicular from the center of a circle to a chord bisect the chord. That means we have to prove AP is equal to PB. Let us do a bit construction. Let us join this OA and OB. Join OA and OB. Again, let us consider this triangle and this triangle. Consider triangle OPA and triangle OPB. OPA and OPB. Since angle OPA is equal to angle OPB, we know that OPA is equal to OPB because both are 90 degree, each 90 degree. Because if OP is perpendicular to AB, that means this angle is equal to this angle, each 90 degree. Then I'll say OA is equal to OB. OA is equal to OB, radii of the same circle. Radii of the same circle. Then one more thing I'll do, OP is equal to OP. OP line, say OP is the side of triangle OPA and OP is the side of triangle OPB as well. So OP is equal to OP common. Therefore, I can say triangle OPA is congruent to triangle OPB by right angle hypotenuse side, because OA is the hypotenuse of this triangle. So it's RHS, right angle hypotenuse side. Then I'll say AP is equal to PB. AP is equal to PB. Now since we proved that this triangle is congruent to this triangle by right angle hypotenuse side, congruency axiom, then we can say AP is equal to PB. AP is equal to PB by CPCTC. And we are done. Hence, proved. Quadrate demonstrandum. Okay, make a note. Now after 10.3, we have theorem 10.4, which says the line drawn through the center of a circle to bisect a chord is perpendicular to the chord. It is similar to the previous one, but the converse of the previous one. Theorem 10.3 was the perpendicular from the chord, from the center of the circle bisects the chord. Now it's the 10.4 is the converse of 10.3. So you can do it in a similar way. It is similar to the previous one. Make two triangles and prove them that they are congruent, then you will get the result. Then I have theorem 10.5. It says there is one and only one circle passing through three given non-collinear points. Passing through three given non-collinear points. There is one and only one circle passing through three given non-collinear points. That means if there are three non-collinear points, for example, here is 1 point, this is 1 point, and let us say here 1 point. These 3 points are non-collinear points because they are not in the alignment. So these are non-collinear points. Now, theorem says that there is only one possible circle which can go through these all three non-collinear points. There cannot be one more circle which intersects these 3 points unless there is a circle which coincides this circle. That means it's similar to the first one. So we need to prove this. What we do, we'll prove this by construction like this. If I'll join this and if I'll join this, let me show it here. If I have 3 non-collinear points, joining this and if I'll join this, if I name them, for example, say like this, P, Q, R. Now let us draw the perpendicular bisector of PQ. You know how to draw a perpendicular bisector. From with P as center and radius more than half. If you have a line segment like this or line like this, you need to draw the perpendicular bisector for this line segment. You do like this. You know that from with this as center, radius more than half, one arc here, one arc here. Then with this as center, this point, one arc intersecting this and this, then join this, you will get the perpendicular bisector. That means this line will be perpendicular as well as bisector of the line segment. So do the same thing here, draw the perpendicular bisector of PQ. So it will be like this. You can draw it easily with your compass and pencil. So draw the perpendicular bisector like this. Similarly, draw the perpendicular bisector for QR. So you'll go like this. So it will be somewhat like this. Now, the point where these two perpendicular bisectors intersect, this point will be the center of the circle. And you can check it by verifying the radius. It is all throughout. Now, with this as center, and you will get the distance from this and this radius, and draw a circle. It will coincide this circle. So this is the center of the circle, and we have only one center, and one center is for this circle, and there is no other possible circle which can go through these PQR. So we proved by construction that there is only one circle which passes through PQR, and PQR were non-collinear points. So that's it. Then we have theorem 10.6, which says equal chords of a circle are equidistant from its center. If I have a circle, equal chords are equidistant from the center. Equal chords of a circle or of two congruent circles. If you have two congruent circles, results is same in that as well. So equal chords of a circle are equidistant from the center. See, if I have this chord and I have one more chord, it says equal chords. That means this chord is equal to this chord. If I name this AB and name this PQ, now AB is equal to PQ. So what's given? What's given? A circle with center O. A circle with center O with AB and PQ, its chords. AB and PQ, its chords, such that AB is equal to PQ. Such that AB is equal to PQ. This is given. Now we need to prove that these equal chords are equidistant from the center, and we take distance. Equidistant means distance from center to the chord, and you know that we take distance, the perpendicular distance always. So this is a perpendicular distance, and this is a perpendicular distance of this point. Let us say this point is M, this point is N. So we need to prove that OM is equal to ON. To prove OM is equal to ON. And here you can write and OM is perpendicular to AB, ON is perpendicular to PQ. So we are going to prove OM is equal to ON. OM is equal to ON. Let us have a construction. join this and let us join this. Join OB and OQ. Join OB and OQ. Proof. First of all, what we'll do, since OM is perpendicular to AB, OM is perpendicular to AB, it's given. We just proved in Theorem 10.3 or so that a perpendicular drawn from the center of a circle to the chord bisects the chord. So this is a perpendicular from the center to the chord, it will bisect the chord. That means AM is equal to MB. We just proved that. So OM is perpendicular to AB, which implies that AM is equal to MB, and reason is perpendicular from the center to the chord bisects the chord, to the chord bisects the chord. Similarly, you can say PN, because ON is a chord, PQ is a chord, ON is perpendicular from the center. So perpendicular from the center to the chord bisects the chord. So PN is equal to NQ. PN is equal to NQ. Now consider triangle OMB and triangle ONQ. Consider triangle OMB and triangle ONQ. Since I can say angle OMB is equal to angle ONQ. OMB, this angle is equal to this angle, each 90 degree, because both are formed by the perpendicular, each 90 degree. Then I'll say OB is equal to OQ. OB is equal to OQ. Reason? Radii of the same circle, because OB is the radius of circle, OQ is radius of circle as well. So OB is equal to OQ, radii of the same circle. Radii of the same circle. Then I'll say MB is equal to NQ. MB is equal to NQ. How? See, as AB is equal to PQ, AB is equal to PQ because it's given that these are equal chords. AB is equal to PQ. Now if AB is equal to PQ, you know that if wholes are equal, halves are equal. That means AB is equal to PQ, half of AB will be equal to half of PQ, and half of AB is MB because we just proved AM is equal to MB. So AB is equal to PQ implies half of AB is equal to half of PQ implies half of AB is MB. Half of AB is MB. Or there is no need to write that one. AB is equal to PQ implies half of AB is equal to half of PQ, and we know half of AB is MB and half of PQ is NQ. Therefore, triangle OMB is congruent to triangle ONQ. ONQ by right angle, hypotenuse, side. Because this is the hypotenuse of this triangle. Right angle, hypotenuse, side. Then I can say, if this triangle is congruent to this triangle, then I can say OM is equal to ON by CPCTC. Hence, proved. That's it. Okay, make a note.